Problem number 32 says we've got a classroom building that has 7 doors, and how many ways can a student enter by one door and exit by a different door? Well, it seems to me we have 2 decisions to make. Which door should we enter, and which door should we use to exit? So we have the 7 doors, so we can use any one of these 7 doors to enter, times. Now, I have to use a different door to exit according to the problem. So there were 7 doors altogether. I already used one, so I can't use that one again. I can't go out the same way I came in. So now there are only 6 doors left. So it seems to be 42 different ways that we can do this. Problem number 38 says that a furniture manufacturer makes 3 types of upholstered chairs and offers 20 fabrics. How many different chairs are possible? So just imagine yourself going in to this manufacturer and trying to choose a chair. I see it as there's 2 decisions we have to make. First of all, what type of chair do we want? And then once we choose the chair, what type of fabric do we want to put on it? So we're told that the manufacturer makes 3 different types of chairs. So we have 3 ways to choose the chair. And then there's 20 different fabrics. So we have 20 ways to make that decision. So I think there are 60 different ways we could make a chair. Now in problem 39, it says there's 6 houses in a row. 1, 2, 3, 4, 5, 6. And we're going to paint each one with one of these colors. We can choose from red, blue, green, and yellow. We want to know how many different ways can the houses be painted so that no 2 adjacent houses are the same color. So I'm taking that to mean like this. We could not have like these 2 houses right here. They can't be both reds, or this one here and this one here can't be green, or this one here and this one here can't be yellow. They all have, whatever this one is, this and this have to be a different color. So I think a good place to start is right here with the first house. Now the first house has nothing on this side, so we can paint this house any of these 4 colors. So let's just make a choice here. We can make any color there, so we have 4 choices. And now our choice for this house, we have 3 choices here, right? Because this house has to be a different color than this one. So whatever we used here, we cannot use here. So now we have 3 choices. So let's write that in. We'll have 3 choices here. Now, for this house just cannot be this color. So whatever color this is, this one has to be different. So if this one here was yellow, this one here could be any one of these 3. So we have 3 choices here, and again 3 choices here, the same reasoning, 3 choices here. And if we multiply those together, we get 972. Problem number 42 asks us this question. If Fred has 10 different pairs of shoes, and how many ways can he put on a pair of shoes that do not match? I'm going to look at it this way. Fred puts on a first shoe and then a second shoe. And so when I'm thinking about this, Fred could put on, well, there's 10 pairs, right? So there's 20 shoes altogether. So Fred could put on any one of those 20 shoes. Then there's 19 shoes left. But one of those 19 matches this one. So if we toss out that match, then there's really only 18 shoes from which Fred can choose. So that multiplication gives us 360 ways. But it doesn't say this in this problem. It doesn't say that the shoes have to match your feet. So you could have maybe a left shoe and then a right shoe. Now that's what this counts up here. So, Fred could have picked a left shoe and then another left shoe. So if we just think that that's not going to work, then our count is going to look like this. There's still 20 shoes that Fred could choose for the first shoe. Now, for the next choice, let's think this way. Whatever shoe this is, if this is a left foot or a right foot, we want the opposite foot over here. So there's going to be, how many choices do we have for this one? Well, there was 20, say you had 20 left shoes, so there's 10 right shoes left. one of them is going to be a match to this left one. So if we take that match out, then there's really only 9 shoes left. That gives us 180 ways. So at first, if it doesn't matter, you have 2 left shoes or 2 right shoes on, that's going to be this count. But if you want 1 left and 1 right, then it's going to be this count. So in this problem, number 46, what we've got going on is this. How many ways can a milkman deliver 10 distinguishable bottles of milk on a street containing 5 houses? So just imagine that you're in this truck and you're delivering the milk and you're looking at your 10 bottles, and then you come up this street. You got some decisions to make. In fact, you have to make 10 decisions. You have, where am I going to put the first bottle? So I have that decision. The second bottle, the third bottle, the fourth, fifth, 6th, 7th, 8th, 9th, 10th. So how many ways can I make that first decision? So I'm looking at that first bottle. There's 5 houses, so I could drop that bottle off at any one of these 5 houses, at any one of the 5 houses. Then we come to the second bottle, right? The first bottle's gone. You come to the second bottle. Well, I could still drop that one off at any one of the 5 houses. So I have 5 choices for that bottle. And then I come to the third bottle. Where should I drop the third bottle? Well, I could drop the third bottle at any one of the 5 houses. So that's going to be a 5. In fact, it's going to be 5s all the way through. So what we're going to get here is 5 to the 10th. And 5 to the 10th, I actually did that on my calculator, but I've forgotten what it is, so I have to do it again. So 5 raised to the 10th is 9, 7, 6, 5, 6, 2, 5, a comma here and a comma here. 9,765,625 ways to do this. So I put 5s here. In every one of these positions I put 5 because there's nothing in the problem that says that the bottles have to go to different houses.